Thank you for the introduction. So I'm presenting the project ROS-MDD, which is about ROS2 code generation and round-trip hour engineering for RobMoSys models. It's a project that initially had two partners. On the one hand, CEA list, on the other, Acutronic Robotics. And well, the initial objective was to provide, on the one hand, the ROS2 code generation based on RobMoSys, and I will tell a bit more about RobMoSys later on, and to make the link between this RobMoSys approach and the ATRIM approach that has been proposed by Acutronics Robotics. So ATRIM is hardware resource modeling, the idea to standardize this. And the second objective was to support round-trip engineering, so that we can go also from existing systems back to models, and well, with the objective that we can use then RobMoSys tooling to work with the systems. And we want to explore the opportunities and the community that we can improve ROS2 with respect to composability, predictability. There was also the aspect of real-time and safety by eventually extensions of the ROS2 middleware. However, Acutronic, unfortunately, it went out of business. So we had to switch the focus a bit. So we had to switch the focus from the ATRIM support to ROS2 in general, and we had to adapt our use cases. So there's still the focus on ROS2 code generation based on RobMoSys modeling, and the aspect of having a reverse and round-trip engineering, there was no impact. And we have a look at the possibility to model high-level task specifications based on behavior trees with associated safety and real-time support. So there was more focus on safety aspects. But unfortunately, we don't have this nice Mara robot that would have been supplied by Acutronics. So instead of having the Mara case study, we looked at two other case studies. On the one hand, that was a Navigation 2 case study, which we executed in a simulator. On the other hand, we used our CEA pilot that we used in the RobMoSys project. So this is a pick-and-place application with this EasyBot, a collaborative robot. And we studied the possibility to look at the behavior tree execution in this context. So first a few words about Papyrus and also Papyrus for robotics. So Papyrus itself is a general purpose model-based engineering tool, principally for UML and SysML. There are also some other extensions, for instance, FUML, executable UML, and FMI. And a good thing about this tool that it's customizable to address specific domain concerns. So we can, for instance, adapt the model explorers, diagrams, and well, there's a lot of ways you can adapt it. And in this context, we have done customization of this tool for the robotics domain. You can here find also some information on the slides about testimonials, about documentation. And in case of Papyrus for robotics, well, there is a principal address here, is eclipse.org Papyrus, and then you can navigate to the robotics component. So what is Papyrus for robotics? It is a RobMoSys aligned modeling front end and a tool with code generation, and there are also some assessment possibilities for the robotic domain. And there is a European project called RobMoSys, in which we are part of, and like ROSIN, this is also a project with some cascade funding. So I will later talk about some sub-projects that were also contributing to Papyrus for Robotics, like ROS-MDD is contributing to ROSIN. So goal of this RobMoSys project is to have composable models and software for robotic systems. It means that you have some information, so you have different artifacts. You have, for instance, a component design, you have an assembly, you have some definition of services, and you have different stakeholders. And RobMoSys is done in a way that all these different models are composable, and you can thus profit from having different people working, for instance, on a component definition, then reusing this component definition, applying some validation and verification means, and eventually go to code generation. And in order to do so, we have different views, and we have a kind of pyramid in which we look at the different services or different aspects on the systems. And there was well, quite well, this an important distinction is a distinction between what we call tier 2 and tier 3. At tier 2, at the level of domain experts. So in this case, domain expert defines services. Well, if you are familiar with ROS, you know that we have all these definition of messages and services that are shipped with a ROS2 installation. And the idea is that in order to get reusable and composable systems, that you kind of standardize these services within the domain so that everyone speaks the same language. If someone provides a camera or an image service, then we have existing definitions of the messages and services coming with it. And so we can achieve interoperable components. And we have a similar thing on what is called a skill. A skill is something like a basic capability of a robot or robotic system. For instance, if I want to do a navigation, then it's a basic skill is to go to a specified coordinates. And for a user, the tier 3 it's more interesting. So on the one hand, there are component definitions that are complying with different needs. Well, some of them might be kind of standardized as well. And then there is a system builder that uses existing component definition to create a system, eventually creating code. And there is also someone who defines a robotic task. A robotic task is not in the sense of an operating task, but a high-level description of a task to fulfill, for instance, to pick up a pile of papers from a place A and transport it to a place B. Could be a high-level behavior that is then broken down in different steps in which these previous skill definitions play a role. And there's also a link with a risk assessment, because when I execute some of these skills, there are risks that are associated with it. And by doing this on the model level, I can then gain more confidence in my system. So let's know that looks in detail by here. there are a lot of different videos that we have done that cover the aspects of these different modeling aspects. And let us now look in as an example that some of you might know. In ROS, there is a navigation 2 stack. And as part of the work that we did in ROS-MDD, we added the capability to Papyrus for Robotics that we can reverse a system, an existing system. So we don't have to start at 0, but we can do a reverse engineering step and then obtain here, in this case, an assembly which has been automatically produced. Well, this diagram, there's some manual layouts that we have done. That's the components, and now the system itself has been reversed from a running system. So there are some functions that, on the one hand, look at the source code, but on the other hand, also look at the running system, see which nodes are active, to see who communicates with whom. Coming back more to the definition of a single component first. So what you see here on the right-hand side is the AMCL node. That is a component within the navigation 2 system. So this is a Monte Carlo simulation, and this component has different services that it offers and that are also used, on which it depends from other component. So here on the left, just by convention, I placed some incoming data flow ports. On the right-hand side, there are outgoing data flow ports, and below you see some service ports. And these service ports reference service definitions. In our case, the service definitions have been reversed from ROS2. So if you know ROS, you see something that you already know here, different packages. For instance, the geometry message package or the navigation message package. And you can you have these services available at the model level, and you can reference them to build your component. And the component has also, well, an internal activity. Well, it was not shown in the previous slide, but here you see that there are some internal activities, and an activity in turn can contain some functions. So that is a moment where you say, when I'm going to implement it, I will associate code with it. So here on the left, you see some activities. You also see here a parameter block, and here on the model level, when you are in the component, you can have in the property view different options. Here you can see what are the parameters of this component, and you see that the AMCL node has a lot of a lot of configuration parameters along with their default value. So what you see here below is this parameter box with the default values, and what you see on the right is an option that we added because some people are a bit reluctant to use model-driven tools. So they like to do things on the code level. So we offer the possibility to open an Eclipse CDT editor, and it's opened on the generated codes. You see here codes that we generated for this AMCL component, and the corresponding code to these parameter declarations. And if a description is edited here, or if the type is changed, then this is immediately updated in the model as well. So that is a quite good mechanism for people that prefer to do some changes on the model level. And of course, for the actual code that is added later on, it makes more sense to do that later on the CDT level in C++ with the C++ editor. And besides of the source code for each node, or well, in RobMoSys terminology, we call that components, we are generating also the build and the launch files. So you get a package XML, a CNEC list text, and we configure an Eclipse CDT project to use Qualcomm with the appropriate configuration. We also generate launch scripts that contain remappings. Why are remappings necessary? Well, look at an example here on the right-hand side. You have a control component in the middle, and you have two different instances of a sensor component, and the component definition level, the sensor component always produces the same topic, but our control wants to get distinguished inputs from, on the one hand, the upper distance sensor and the lower distance sensor, and therefore we are doing remappings in the launch files to correspond to this image you see here in a kind of component assembly, where you explicitly connect ports component with an input port on another component. And the launch script, we also generate a variant that activates components automatically. And of course, we make sure that when you put some parameter configurations on a component, that we generate the appropriate YAML file, which contains then the configurations. And with respect to Eclipse integration, well, what I already told you, there is it's a possibility to open a CDT editor. Something I think which is also quite useful is that you can debug an application using a CDT debugger, and you can launch that then from the environment in which your model tool is started as well. And it's an application can be started then, and you can see how it progresses in the using the console. What I told you before is it's nice to have models. What is the added value to have models? And one of the advantages of having models is that you can combine then the application models with other models. In this case, for safety aspects, we wanted to do a hazard and risk analysis in the context of a task. So if I look here, it's such a pick and place task, and there, what you see here on the right is a behavior tree. So there are different steps, and for each of these steps, there are some skills that are involved, and there is a potential risk for of these operations, because this is a collaborative robot, and there might be an operator that is in an area in which he's not supposed to be. So we can do a hazard and risk analysis in which we, on the model level, have all the potential hazards and can associate that with the skill and the risk. So it's something that helps us to identify and eventually mitigate the possible risk. And if you want to go into detail, there's also a video on this aspect. On this slide, we show how task execution and monitoring is done in principle. So you have a sequencer which corresponds, by the way, quite closely to the sequencer that was also used in the navigation 2 stack. And this sequencer is then coordinating other components. In our case, it's coordinating the EasyBot component the EasyPort robot, and we do the necessity that it's a dynamic connection to with all the components that are involved in such a high-level task. And eventually I will show an example how the gripper is used later, but yeah, for the moment, just continue. As I told you before, there are also some enhancements that are done in other projects. In RobMoSys, it's also a cascade funding project, and we have their so-called ITPs. So the ITPs in RobMoSys is more or less the same thing what an FTP is in ROSIN. It's called Integrated Technical Project, but the idea is the same. This is we have some specific task on which a project can focus, and we had some cascade-funded projects in RobMoSys that were improving Papyrus for robotics. The first one was EITUS, done by Technalia, in which we have the possibility to specify fault injection on the model level, and then you can compare simulated golden execution with a faulty execution. I forgot to say that Akio Plus was another partner in this project, so there was also an industrial involved. And Technalia has a lot of work in the safety context. So beside of the fault injections, they also looked at the possibility to specify assertions and contracts and integrate the Othello language that was done in the SafeCC for Robot project. And there are two other projects in the context of safety as well. In for scope, we have verified system properties. We can specify, for instance, some invariants and link them with elements of the behavior tree. And in for Samara, a link with the hazard and risk analysis capability that was better supported in Papyrus for robotics. So to summarize, what are the contributions to the ROS2 community? We have a model-driven approach, which identifies different roles and stakeholders. We have explicit provided required services. We can generate code. We can also create the necessary build and launch files. And I think this is an added value for people that are non-experts and want to start writing some simple ROS2 nodes. And if they use our tools, they can just start with some examples that we provide, and they don't have to know the details of writing these build files and how to create, for instance, a publisher. They can just provide the and another added value is that we have a link with safety-based considerations. For instance, the possibility to specify assertions and to have an hazard and risk analysis on the level of behavior tree. And a good thing is that you don't have to start from scratch. You have model libraries that concern all the existing standard ROS messages and services. There's also one for within extension in navigation 2, and if you have your own services, you can also start the reversing by mechanisms provided in the tools. And we are just working on a possibility to reverse automatically a whole workspace and have all the nodes that are defined inside as external components. External components means that we are not generating code for these, but we have the necessary definitions on the model level. So if you are using an assembly, you can directly define component instances, configure the parameters, because you have this information at the model level, but you don't necessarily have to generate code because the algorithms are not part of the reverse process. And on this slide, I have an outlook on some future work that we are doing. We are using Papyrus for robotics internally in multiple projects, partly European projects. So it means that we continue to develop the project actively. Eventually, we will also use it in upcoming project proposals. One thing that we identified would be useful, which is currently not supported in RobMoSys, is that you have composite components. So components have some internal components itself with an internal structure. At the moment, you only have this at the system level. And there's also support for automated planning solutions. That is something where we have collaborated with Francisco, who will do the next talks. So there's some synergy to on the behavior tree level to use our tool for planning. And we are thinking about upcoming real-time support and a model of computation with ROS2 and Python CPA. So that is some of the work we would like to do in the future. And yeah, that's the end of my talk. I think it's more interesting if we use the remaining time for questions and showing a video. So do you have questions?
Thanks a lot, Ansgar, for a very insightful talk. Definitely very different approach than what usually ROS developers are used to. So yeah, I'm looking forward to what questions do the audience have for you.
Yeah.
Right. Doesn't seem to be the case. So I have few questions. So definitely, this is a very different way of programming. So how do you think we could, or you could reduce the, let's say, entry-level barrier for developers? So especially in the ROS community, we are used to, we say quick and dirty, you know, like we just want to just start writing code. So how do you think that entry-level barrier, because this seems very complicated, maybe it's not, but how do you think that entry-level barrier can be reduced for newcomers or already existing ROS developers?
Yeah, that's a question, and effectively we have also thought about this problem, and therefore we, on the one hand, we have this integration with Eclipse CDT. So if you want, you can open a CDT editor on the generated code, and you can then do some modifications there. And for writing the algorithms, you're still supposed to do that in C++ as well. We also have some other textual editors. For instance, if you want to define a data type, so something like the occupancy grid here, you also have the possibility to use a textual editor, which gives you, well, it's a bit similar than defining it in C. So if you're coming from programming, I think it should not be too difficult then to edit specific things. But for the starting point, we have the possibility to to just say, okay, I find new example in Eclipse, you get some very simple projects that are already defined. So if you open one of the examples, then you can see how it's done. So you basically draw here your component definition. You see on the right-hand side, you say you want to create a new component definition. You add ports and you choose an existing servers or mess type, and then you can generate code and to do the rest on the code level. So does this answer your question? And of course, I invite all of you to just download the tool, and also from here you can. There's also a documentation section with tells you how to start.
Actually, we have already run out of time, but I have another very quick question. So, of course, modeling makes sense, let's say at a node level or a launch file level, but you also have modeled at a behavior tree level where you have a move or a close gripper. So, especially something like close or open gripper, I think is very hardware specific. So, first of all, how do you let's say hide the implementation part, because multiple grippers might mean different things for what closing a gripper is.
Yeah, you're right. There are different abstraction levels. So there is what we call the skill. The skill is, for instance, to close a gripper, and that is something here which is at a leaf level in the behavior tree. And there is a component behind, and the algorithm or the code of the component takes care of opening and closing a gripper in a half a specific way. And the behavior tree is just doing the orchestration. So we have here different skills that are realized by one or more components. And we have a classical programming of implementation behind these skills. And we have the behavior tree for the coordination level.
Yeah, all right. So do we have more questions to Ansgar? All right, does not seem to be the case. So thanks a lot, Ansgar.